Let's continue with our lecture with the theories of attached growth reactors. In the last class, we have introduced the basic concept of biofilm modeling. The diffusion reaction equation helps determine the substrate profile in the biofilm, and the effectiveness factor approach simplifies the solution for the flux of substrate into the biofilm. Knowing the flux, we should have all the components to solve the mass balance for the attached growth reactors. Although the effectiveness factor approach makes it easy to model one substrate degraded by one biomass, it still has a lot of limitations. The most prominent of which is that the biofilm thickness needs to be assumed, adding uncertainty to the modeling results. To achieve a better estimation of attached growth reactor performance, we can use the pseudo-analytical approach. In pseudo-analytical approach, the solution was found numerically for a special case, the deep biofilm, where the substrate concentration becomes zero before it reaches the substratum. And the solution was extended to other cases with correction terms. The basis for the pseudo-analytical approach is that the flux of substrate into biofilm decreases with the bulk solution substrate concentration. When bulk solution substrate concentration is lower than the threshold, S sub SB min, the flux becomes zero. This is because when bulk substrate concentration is lower than S sub SB min, the growth rate is slower than decay and detachment. The biomass in the biofilm is washed out. This is similar to the S sub S min in CSTR when bulk solution biomass is washed out. The equation for S sub SB min has special significance in a pseudo-analytical approach. Its dimensionless form becomes the Riemann number. We can then write a series of equations to describe the biofilm. The thickness of a biofilm is determined by growth, decay, and detachment. The numerator is the growth determined by yield and substrate flux, and the denominator is the decay and detachment. The diffusion reaction equation that we have seen before describes the substrate mass balance in the biofilm. Equation 3 describes the change of biomass thickness. The thickness increases due to growth and decreases due to decay and detachment. Next equation is a fixed first law describing the flux at the biofilm surface, which is determined by substrate diffusivity in the biofilm and concentration gradient. Lastly, it is a flux of substrate at the stagnant boundary layer determined by the substrate mass transfer coefficient in water and the substrate concentration difference between the bulk solution and the biofilm surface. As I mentioned before, there is no analytical solution for the system of nonlinear differential algebraic equations, but we can solve it numerically for the deep biofilm and extend it to other cases. We can scale the parameters to dimensionless forms to simplify the solution. Solve the deep biofilm numerically, we can express the dimensionless flux with dimensionless substrate concentration S sub SS star, which is S sub SS divided by K sub S. We can then extend the dimensionless deep biofilm flux to other cases where substrate does not decrease to zero, with a factor of psi, which is the degree to which it varies from the ideal deep biofilm. Before finding the expression for psi, let's recall that the dimensionless minimum substrate concentration, or S sub SB min, is a Riemann number. Xi equals to hyperbolic tangent alpha prime times the dimensionless substrate concentration at the biofilm surface, divided by the Riemann number minus 1 to the power of beta prime. And we can express alpha prime and beta prime with Riemann number. Here's how we use the pseudo-analytical approach. We know the substrate concentration in the bulk solution, which is our design goal, we need to calculate the flux of substrate into biofilm to get the reactor mass balance. We should first calculate the dimensionless bulk solution substrate concentration, dimensionless minimum bulk solution substrate concentration, which is also the Riemann number, and the dimensionless mass transfer coefficient. With the first two dimensionless numbers, we can calculate the dimensionless deep biofilm flux, alpha prime, beta prime, and Xi. We can then calculate the dimensionless substrate concentration at the biofilm surface iteratively, with the initial guess for S sub SS star equals to S sub SSB min star plus 10 to negative 6. We can then compute the dimensionless flux and finally convert the dimensionless flux to actual flux. Once we know the flux, we can calculate the biofilm thickness and biofilm surface area. Finally, we can determine the design volume for the reactor. We can set up these steps for a pseudo-analytical approach into a spreadsheet to streamline the calculations. The last approach that I'd like to cover is a normalized loading curve approach. This is essentially the same as the pseudo-analytical approach, but summarizes the results to normalized loading curves. The loading curves is the relationship between S sub SB over S sub SB min and JS over JSR, in which JSR is the reference flux, which is a minimum flux to maintain a deep biofilm. For JSR star, Xi equals to 0.99. We can find the dimensionless JSR or JSR star with the curve in figure 16.12. We also know the dimensionless mass transfer coefficient, S sub SB min, and our design goal, S sub SB. We can determine the flux Js according to the normalized loading curves. These figures are the normalized loading curves showing the relationship between S sub SB over S sub SB min and Js over JSR for different Riemann numbers and KL star values. Again, with Js known, we can calculate the biofilm surface area, thickness, and write the reactor mass balance and determine the reactor volume. As we have covered before, if the substrate concentration is far lower than K sub S, we can approximate Monod equation as a first-order relationship. Then, the diffusion reaction equation becomes a linear second-order differential equation, which can be solved analytically. Solving and transforming that, we can get the expression for the dimensionless flux. On the other hand, if the substrate concentration is much larger than K sub S, the Monod equation can be approximated as a zero-order equation. The diffusion reaction equation can also be solved in this case. The dimensionless zero-order flux equals to the dimensionless biofilm thickness. If the biofilm is reaction limited, meaning that the substrate consumption rate is far lower than the substrate diffusion rate, the biofilm is then fully penetrated. The substrate concentration is constant throughout the depth of the biofilm because as soon as the substrate is consumed within the biofilm, the substrate in the bulk solution diffuses in to fill the vacancy. In this case, the flux is solely controlled by the reaction rate. This expression of dimensionless flux for the fully penetrated biofilm is the Monod equation expressed by dimensionless terms. The previous model considers only one limiting nutrient, but in reality, there can be multiple limiting nutrients. For example, electron acceptors like oxygen or nitrate can be the limiting factor in addition to the electron donors. This is especially true in aerobic attached growth systems, as oxygen has low mass transfer coefficient and diffusivity in water and in biofilm, which can cause oxygen deficiency within the biofilm. To account for two limiting nutrients, two separate mass transport equations interacting with each other needs to be coupled with the double Monod equations. forming two separate mass balances interacting with each other. This complex system of equations are typically solved numerically with the help of computer softwares. This figure shows the concentration profile of ammonia and oxygen in a nitrifying biofilm. At high oxygen concentration, ammonia is depleted in the biofilm while oxygen is not. But as oxygen concentration in the feed solution decreases, oxygen becomes the limiting factor. It is depleted in the biofilm while there is still ammonia at the bottom of the biofilm. In real world, there can also be multiple microbial groups with different substrate and products in the biofilm. In the GDLF book, equations 16.51 to 16.62 describe the model of two microbial groups that do not compete for substrate in the biofilm. It is a simple extension of the one microbial group model. But in reality, there can be interactions between different microbial groups like competition, synergy, cross-feeding, inhibition, etc. So the modeling can be even more complicated. But we will not cover these models in this class. We can utilize a system of interacting equations to solve the flux of multiple substrates, the growth, decay of multiple microbial groups in the biofilm system, like ASM1 for suspended growth systems. We also need computer models to solve that. This is a simple conceptual figure showing the distribution of different microbial groups. Species B has a low mu max, but also a low K sub S. Therefore, can thrive in the deep end of the biofilm, where the substrate concentration is low. Species A, on the other hand, has a high mu max and high K sub S, and thrives at the surface of biofilm, where there is abundant substrate. Also, the percentage of the debris increases as we look deeper into the biofilm as a result of a low growth rate due to low substrate concentration. In the next two classes, we're going to use these theories to investigate two different types of attached growth reactors, the fluidized bed bioreactors and the packed towers.